Hello, and welcome to the first lecture from Chapter 3. Okay, so this is Chapter 3 from the Physics of Everyday Phenomenon, a Conceptual Introduction to Physics, the 10th edition, by Thomas Griffith and Juliet Brosing. Okay, and this is the first lecture in this chapter. All right, so there'll be a series of lectures, 2 or 3 for this chapter. The last chapter, Chapter 2, had 4 lectures for it, which introduced speed, velocity, and acceleration. Okay, so now let's get into what this chapter is all about. Let's go ahead and actually take a look at the textbook. Right. So up here we can see that indeed this is Chapter 3, starting on page 35. Okay, so we have a overview of this chapter and a title which says it's about falling objects in projectile motion. Okay, so falling objects are one-dimensional motion because falling means straight up or straight down. Okay, now interestingly, when we talk about a falling object, it's just an object that's moving one-dimensionally, so only in the y direction, y being a letter we'd associate with vertical motion, okay, like x and y. So we have this object that's only moving in the y direction, no side-to-side motion. Now, being in free fall, a term I'll use quite a bit, doesn't mean that it's necessarily falling. It just means that it's accelerating downwards at gravitational acceleration, okay? So, for example, if I took my flash drive here and I threw it, it would be falling on the way up. It would be falling at the moment that it momentarily is at rest at the top of its motion, right? It's one-dimensional motion. And then it would be falling on the way down, okay? How is it falling the whole way? Because it's accelerating with the exact same acceleration the entire time. It is experiencing a uniform, constant acceleration, an unchanging acceleration of 9.8 meters per second squared, okay? Because we're on the surface of Earth, and it's pointed straight downwards, specifically pointed straight towards the center of the Earth. But since we don't notice that curvature when we're on the Earth due to its massive size, it just is effectively straight down, okay? So that's what we mean by falling objects in free fall. Projectile motion we'll definitely get into the second video. I may have 2 videos dedicated to projectile motion. What that's all about is what the name implies. It's like shooting a cannon or a projectile like in a video game like Angry Birds, right? Where you have to like get the angle just right and get the speed just right in order to get a particular target, okay? That's the idea. That's what projectile motion is about, if we're thinking about it, is we're trying to get to a particular target. Now, it turns out that with the concepts that we have, the way we can calculate changes in velocity and changes in position with constant acceleration, we can find exact quantities of the speed, of the position at any instant in time, or maybe we could solve, instead of plugging in time, we can solve for time, whatever we're asked for in the system. Okay, but it's 2-dimensional, unlike free fall. All right, so there's motion in both x and y, but the only acceleration is in the y direction. So the thing that defines projectile motion and makes it different than, say, like rocket motion or the motion of a plane is those things, rockets and planes that is, they experience a lateral force as well. There is a force in the x direction, a force that's going to be changing the speed in the x direction, right, slowing it down, speeding it up. Now, a projectile doesn't have that. Projectile is only experiencing the acceleration of gravity because it's inert, right? It doesn't carry anything on board with it, right? It isn't like a rocket. Okay, so that's what we mean by a projectile, 2-dimensional motion, but just with that single acceleration, the same single acceleration that defines falling motion. Okay, so you can see in the sections, we've got acceleration due to gravity, just make sure we define that. Okay, then we're going to have tracking a falling object, then beyond free fall, so that means that includes the part of the falling motion that's on the way up. Okay, so I hopefully preempted that confusion by bringing that up right away. You can see that as the third section, kind of the final culmination of thinking about falling motion. All right, so let's go ahead and take a look at some of the slides. Right, let's get into this topic here. All right, so gravity influences motion in a particular way. Which way is that? Okay, gravity, a force. We'll talk more about forces in the next chapter. We keep hinting at them, but we'll officially define them in Chapter 4. But for now, we know there is a force, the force of gravity, that creates the acceleration of gravity. Okay, so when people talk about how heavy you are on the surface of Earth and maybe compare that to how things have different weights on different planets, maybe you've heard that, or maybe you've heard how people are so much lighter on the moon, those few astronauts that have been to the moon, okay, decades ago, those astronauts were so much lighter because the gravitational force is much less on the moon. It's about 1/6 at what it is on Earth due to the smaller size and mass of the moon compared to Earth. That means that the gravitational acceleration is also 1/6 as strong, okay? So that's the idea, is that there's one value on the surface of any large celestial body, like a moon or a planet, okay? So the idea then is that that gravitational acceleration is absolutely shared by every single object, okay? There's nothing special about it. The only thing that defines it is the planet, okay? Now that's because the effect of the object and the gravitational pull it has on Earth, and therefore the net acceleration of the system, including the acceleration of the Earth, right? From, say, you know, dropping a brick here, right? How much does the brick pull the Earth towards it? Well, technically it does, right? But it's pulling it towards it at a rate that is a trillion times smaller than an atom per second, an absolutely unmeasurable amount. Okay, so effectively and for all intents and purposes, the Earth does not move as an effect of the gravitational pull of the brick. Instead, the much greater mass, right? A trillion kilograms, 10 to the 24 kilograms, that's the mass of the Earth in the metric system, 10 to the 24 kilograms. That mass of the Earth, okay, that creates a huge pull, huge force, and that force greatly overwhelms whatever, you know, small gravitational force from a small, you know, macroscopic object, okay? So point being, because of that, it is a totally reasonable assumption, I mean, paramountly reasonable, to say that every object accelerates at the same rate towards the surface of Earth, okay? Doesn't matter what that object is, from a rhinoceros, I don't know why you're dropping a rhinoceros, to a feather, to a brick. Now, right? In reality, certain objects that experience a lot of air resistance due to their shape, right? Things like feathers, okay? It's not noticeable that they fall at the same rate, right? Because that air resistance is making everything, you know, kind of behave differently, right? We live in a fluid. Yeah, it's a low density fluid, the air, compared to much higher density fluid known as water. In fact, it's a difference of 1,000. Water's 1,000 times denser than air. But we're still surrounded by air, and that has a really big effect on how things behave, right? In particular, certain things, low mass, high surface area, okay? So, do the different shapes and different masses affect the free fall? Theoretically, they shouldn't, right? Or theoretically, in a vacuum, they shouldn't. We know that we can actually quantify our resistance and say that yes, the shape does matter, okay, as just the surface area to mass ratio, okay? But ideally, everything should fall at the same rate, okay? So the acceleration due to gravity, okay? So this is our special case of acceleration. This is a uniform and constant acceleration. So we're going to use the formulas that we saw in section 2.5. Please review those formulas in section 2.5. Earth exerts a gravitational force on objects that is attractive, okay? By the way, gravitational force, always an attractive force, okay? Unlike the electrostatic force. Near Earth's surface, this force produces a constant acceleration downwards. Excellent, okay? Unchanging. To measure this acceleration, we need to slow down the action, okay? It's difficult to measure. It's fast enough, right, that you either have to draw something really far off a really big cliff, right, kind of actually accurately measure it, or to use modern techniques like fast, you know, film rates, right, where you can actually analyze something maybe 60 times per second or 120 times per second, right? Well, 500 years ago, when Galileo was performing experiments to show that there's this thing that is constant for all objects, he couldn't do that, right? He couldn't use, you know, high-speed film. It certainly didn't exist. So he was able to measure this acceleration of gravity at a smaller fraction using rolling motion, okay? So he was able to create these ramps, right? Not particularly steep, because he needed things to kind of roll uniformly and relatively slow. And with all these different ramps, he was able to show that the rolling motion was not dependent on the object that was rolling, but instead was dependent only on the slope, right? So the acceleration was always some proportion of the slope, and it was trending towards a slope that was vertical, right? Which he couldn't actually measure, but he could see the trend, and towards vertical, that acceleration approaches some final value, right? For all the balls, everything that was rolled, okay? So he was able to find that gravitational acceleration is one particular value shared by all objects in the absence of, you know, air resistance or even friction, okay? So, right, that's the idea, is that gravitational acceleration shared by everything. Definitely works for free fall. That's a great simple case of it because it's straight up and down, easy to think about what we're talking about here, okay? Truly one-dimensional. But does it also work on inclined planes, like the ones that I was talking about that Galileo used, this idea of rolling objects? Yes, it does, right? Here's a really simple inclined plane with this ruler slightly lifted up on one end due to the pencil underneath it, right? And then the lower end over here resting on the table. The handy trough in the middle of the roller will allow for a marble to roll down it, all right? And this marble will roll down, Okay, is it going to roll down with the full gravitational acceleration that I told you is 9.8 meters per second squared? No. It's going to roll down with some fraction of that is directly proportional to the angle of the ramp and nothing else. Okay, ideally. All right. Now, things like friction, things like air resistance are going to affect that ideal result. All right. Now, but you did it in a vacuum, okay, and you did it with a surface that was, sufficiently smooth, then you're going to actually get a result that matches the theory. Okay. On that note, what happens when we actually go to a planet without air resistance, a planet without an atmosphere? Actually, not a planet at all, a moon, our moon. Well, here's a picture of an astronaut on the moon dropping two different objects and observing, right, hopefully, that they fall at the same rate, thus proving this concept that there is such a thing as shared gravitational acceleration, kind of this, which is a backbone of the theory of gravity itself, okay? So this is kind of an observation, this idea that gravitational acceleration is constant, that we'll see then leads to other theories, namely the universal theory of gravitation, that all mass attracts other mass. All right, so let's take a quick look at the video.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon.
Yeah, falcon mission.
And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
Yeah.
How about that?
You see?
They'll hit the ground at the same time. How about that?
Okay. So you can see in the grainy photo, hammer, feather, drop both at the same rate. Not as fast as they drop on Earth, right? So we can actually kind of see it without a slowed down video, okay? Appreciate it. But still fairly fast, right? 1/6 of gravity, so things still noticeably fall. But you notice that the feather and the hammer really fell at the same rate, okay? It doesn't matter that that feather's much lighter. You get rid of the air resistance that normally would define, or I should say on the surface of Earth defines the motion of a feather, right? In the atmosphere-less, no atmosphere surface of the moon, yeah, fall at the same rate, okay? So that indeed is the concept of shared gravitational acceleration, okay? So we can see that rate of movement manifest itself in the type of graphs that we saw at the end of the last chapter, okay? Because this is constant acceleration, which means it leads to linear velocity, so a diagonal line, okay? Which then leads to parabolic position, right? That's the parabola of position. The position is growing over time, and it's growing at a faster and faster rate, okay? All because of constant acceleration. So we saw that graphically. Another way to think about that pictorially is to look at this stroboscope, which is just looking at kind of flashes and overlaying images. So we can see that we're essentially taking an image equal times, right? So our time between images is unchanging. But since the ball is moving faster and faster as it falls, as things do, the gap that it covers in that same amount of time grows. So then what this stroboscope shows is that type of motion, that accelerating motion, right? First it's moving slowly, shown as the smaller gaps between the ball, right? But then the ball is able to cover bigger and bigger ground, okay? All right. Okay, so when we look at this, we could then think about the average velocity over this period of time because the velocity is increasing linearly, okay? So it's precisely that idea of having this average growing velocity, okay? And we could come up with the average velocity at different moments in time, okay? So here, this is actually for the first, this is collecting the data, okay? So I said this would be the average velocity over the total time. It's actually not. This is just the average velocity from 2 points. So it says here that we're going to compare between the second and third flash, right? So that would be the second and third image. And we're just going to look at their positions. So we've scaled the image. We know how many pixels are equivalent to some centimeter distance usually. Okay, so we have 4.8 to 1.2. That would be like the center of the ball measured at 4.8 to the center of the ball here measured at 1.2. Okay, so it's a vertical distance of 3.6. We know that the elapsed time between any two flashes, this example being no exception, is a 20th of a second or 0.05 seconds. So then we simply take the average velocity of that segment. Okay, and there's no data in between, so this is as much as we can average, right? We're limited of how many flashes we have. Okay, fact that we're only flashing 20 times per second. It'd be great if maybe we were flashing 100 times per second, but we weren't, right? So then we get the average velocity in a segment of time is 72 centimeters per second. Okay? Now that will be the slowest speed, right? Because any subsequent speed, we're going to have a bigger distance, but the same elapsed time, right? So then let's see. So we can see, right, our elapsed time, right, grows, but the difference between any two of them is always going to be 0.05, right? So we're always interested in the difference of time. This is just the running time on this this column here, the furthest left column. And then the furthest, or the middle column, is the running position, just the current position, okay? Starting at 0, right? Growing as we move down. So 60 centimeters here is the vertical position measured from kind of this clamp up here. That would be, y equals 0, all right? And then growing in the positive direction downwards, which is not typical for, it's called positive downwards, but here we are, right? We're totally allowed to, right? More convenient to do so, all right? And then the average velocity we see, right, in between any segment is growing, right? 24, 72, so on. This is the one we already talked about, right? It's 24 would be the previous one. So we have a growing average velocity. That average velocity, if we were then to graph it as a function of time, we see that it matches what we'd expect from the theory discussed at the end of the previous chapter, okay? Because that was just in general constant acceleration. This is particularly gravity as constant acceleration, okay? So what we see then, again, is that we have this linear, right, this diagonal line for that growth of the velocity. The ball is speeding up as it falls, okay? All right, so the slope of the line is constant. What is the slope? Well, it's acceleration, okay? The slope of that line is a acceleration. It's a single value. It's not a function of time. It's a constant, just a number, okay? And if we looked at it, right, so then we're simply going to do rise over run. We're going to choose the average slope. A great thing you could do here, rather than just literally looking at the two endpoints, is to do a more complicated average, like is done in Excel with something called an R-squared value in a linear fit. It's just a better average, right? Because you're kind of comparing more things. But when you do that, you'd still get some slope, no matter how you equate that slope, how you calculate that slope. And here, so we can see it comes out. We are given very accurate data, right, in this example, to 980 centimeters per second squared. Okay. Now it's going to be in centimeters because all our measurements were in centimeters. Okay. But we don't want to leave this in centimeters per second squared. Those are not the base units that we typically use in physics. Meters per second squared are. So we see we just convert it over. We know there's 100 centimeters per meter. So the conversion is simply move the decimal place over 2 to the left, or in other words, divide by 100. So if you divide 980 by 100, you get 9.8. Well, there you go. That is the value, the accepted value, in fact, of gravitational acceleration. Here, right, shown in a mock experiment, a type of experiment that could actually, garner you that value, right? This is how people find the value. This is the type of experiment I ask students to do, to carry out in the laboratory or remotely at home, to actually find this themselves, and is totally something you can do, okay? So that's the idea. That is acceleration, right, resulting in linear growth of velocity, right? So the diagram here shows position in 1/10 second intervals of a ball moving from the left to the right. So this picture, kind of like the stroboscope, it should tell us that there's a acceleration or not. Is there? Think about if you're understanding here. You should be able to answer this one. Does this show acceleration? Okay, no. Okay, it shows zero acceleration, which is a form of acceleration, but it's not showing a non-zero acceleration. Okay, this is a case where the velocity is constant and the acceleration is zero. Okay, so this would be no acceleration, right? What about these cases? All right. So after either or both of these, is the ball accelerated, right? So in this case, right, we can see in A, the distances between, intervals is small at first and then grows. And in B, we had big intervals in it than the smaller intervals, right? Distance intervals, right? And again, every one of these is like a strobe, is always the same elapsed time. So I bet you can think what's going on, right? Okay, I won't say anything, just think of an answer, think what's going on, and then we'll discuss. Okay, make sure you have an answer locked in. Thought about it carefully? Okay, you ready? Okay, it's actually both. And I bring that up because it's one of those common pitfalls I talked about. People tend to think, right, from everyday language, that acceleration is only speeding up. And then there's this thing called deceleration that's slowing down. Well, no, there's just positive acceleration and negative acceleration depending on however you defined your coordinate system. In fact, we just saw an example where down was defined as positive, right? Well, doesn't matter, right? It's just acceleration. Okay, so in this case, right, in case A, we have an acceleration in terms of the vectors that is pointing the opposite direction of the velocity. So it's actually causing, the same direction as the velocity. And we know that because it's causing it to speed up, right? This is in the case of speeding up, okay? The magnitude of the velocity is growing. and B, the magnitude of the velocity is decreasing, that would tell us if we were to look at the 1D vectors for velocity, the initial velocity pointing towards the right on the screen, the initial acceleration would actually have to point backwards towards the left on the screen, because only that type of backwards pointing acceleration could cause the motion that we see. Slowing down. Still an acceleration though, okay? Just one that points the other way, okay? So how do dropped objects behave, right? They would fall at the same rate. As we saw in a vacuum, there's a cool video that actually has this giant vacuum that NASA uses, so you can do it on Earth as well, okay? But you do have to have a really good vacuum to really show a feather and a brick fall at the same rate. But we saw that it works pretty easily if you can get yourself to the surface of the moon to demonstrate it there with a hammer and a feather, okay? Right? So that's the idea, is all things should fall at that same rate. So without air resistance or ignoring it, right? And there are plenty of situations, by the way, for like massive things like a bowling ball, it's the gravitational force is so much bigger than the air resistance force that we could practically ignore it, right? So there are a lot of systems, right? There are other systems like a parachute where you can't, right? It's dominated by the air resistance force. So it depends, right? But in systems where we can't ignore air resistance, we have this value of gravitational acceleration on the surface of Earth, okay, taken as a global average of 9.8. Okay, meters per second squared. Sometimes we can round it to 10. If you're ever going to actually do that in a problem, I'll tell you to either use the rounded value or not. Okay, so in general, with the rounded value, a cool way of thinking about it that I think justifies rounding it sometimes is thinking that every second of free fall, the velocity is 10 meters per second faster, right? So you start at 0, after 1 second of free fall, you move 10 meters per second, after 2 seconds of free fall, you move 20 meters per second, and so on, right? Pretty neat idea, okay? So here we have this idea, right? How does that equate to miles per hour? Well, it's pretty fast, right? Things speed up really quickly, right? So we can see, right, that after just 3 seconds of free fall, in the metric system, your speed is 30 meters per second, which might be hard to visualize, right? Well, that's equivalent to about 70 miles per hour. That's not hard to visualize. Wow, you're moving highway speeds, right, after just 3 seconds of free fall, right? That's why without air resistance, free fall is a really big deal, and why you don't want to, jump without a parachute, right? Now, even without a parachute, you'll eventually reach something called terminal velocity, but it's going to be hundreds of meters per second, okay? Here is the actual equation showing how far you move, okay? This is an equation that we derive in the last video, so the 4th video from chapter 2. Okay, I talk about justifying where this equation comes from. This is an actual equation you can use to calculate distance as a function of time for any constant acceleration. In this case, we would use the special case, right, the very useful case of gravity on Earth, right, gravitational acceleration on Earth. Okay. When you say gravity on Earth, right, do you mean the force or the acceleration? So I try to specify. Here, obviously, we're talking about the acceleration. Right? Here we're using the rounded value of 10. Okay. So that gives you right there, right? You can find after 1 second of free fall, because that's the input here, square it, doesn't matter for 1 squared is still 1, right? Then multiply by 10, take half of that, you find that after 1 second of free fall, you've moved 5 meters. You can continue to plug in, by the way, try this, plug in 2 seconds, right? You plug in 2 seconds, you're going to get a distance of, right, so right here, at 2 seconds, you have a distance of 20 meters, see? If you plug in 1.5 seconds, by the way, you get 11.3 meters, okay? Plug them all in, test it out, okay? Use 10, use 9.8, up to you, okay? So, let's see, I want to get to throwing the ball downwards, it's more cases, okay? So so we'll do this slide. We're going to stop before we get to considering more complicated cases of free fall, right? This idea, because so far we're just dropping something. It's a great way to start thinking about this idea, right, of constant acceleration, gravity pulling things down. But obviously we can do more than drop. We can throw upwards. I mentioned that. We can also throw downwards. How does that affect motion, right? Okay, so quick concept question, and then we'll get to that stopping point and talk about more complicated one-dimensional free fall in the next video. So the velocity versus time graph for a certain falling object is shown, okay? So it's velocity versus time. Is the acceleration of this object constant? Okay, think carefully. Think about what we've been talking about, constant acceleration. What type of velocity does that result in? Does that match this graph? Definitely not, okay? Constant acceleration creates a linear graph of velocity, okay? This graph kind of looks like a parabola, right? Like we'd see for constant acceleration if we were looking at a graph of position, vertical position, right? But no, this is velocity we're showing. So this is definitely not constant acceleration. This would be something that requires a non-constant acceleration, which would be a non-constant force, which is something other than gravity. It's like a rocket, okay? Okay? So, right, then what we'll pick up on in the next video is considering vertical motion, the constant acceleration being that of gravity on the surface of Earth, so that's that special value of 9.8 meters per second squared, but adding one little wrinkle, one little extra idea, and that's that we can give our object an initial velocity, okay? We can throw it, straight down and give an initial velocity that is in agreement in sign to the sign of the acceleration, because they both point in the same direction, or we can throw it up, in which case the initial velocity is opposite, it's positive, whereas acceleration would be negative, or vice versa, by the way, however you want to define your coordinate system. But I'm going to do an example with that, okay? We'll actually do an example that in addition to whatever, the examples they have in the slides, okay? I think I really need to show that to you, go through some of the cases on this one, make sure it's clear, all right? So we'll be talking more about those kind of extra conditions, extra considerations for free fall motion in the next video. I hope this first video introducing gravitational acceleration and free fall has been interesting and informative. Please check back in for more lecture videos on Chapter 3. Bye for now.